theory. The theory is that when we feed a bunch of turn detection specific data sets through a training process on that model, we're getting two things. The model is learning acoustic patterns, like if I draw out a word, or if I have a rising intonation, or if I have a particular sort of pattern of syllables at the end of my phrases that indicate that I'm not done talking, the model is learning that. The model is also, we're also leveraging all the weights in the pre-trained version of the model that have to do with like language structure. So we're also getting the language structure stuff that you get from a text-only approach. Welcome. I'm Quinn Altman Kramer, and I work at a company called Daily. We make real-time audio and video infrastructure for voice and video and AI. And these days I work a lot on an open source project called PipeCat, which has become a very widely used agent framework for building real-time multimodal AI things. We will talk some about Pipe in this course, partly because it's open source and partly because it's widely used and partly because it's the lens through which I tend to view real-time voice and multimodal AI. But this course is platform neutral. We're going to talk about a lot of tools. You'll hear about VAPI and Layer Code, which are two full-featured voice AI infrastructure platforms. We'll have a session about Fast RTC, which is a really cool Hugging Face framework, and lots of other tools as well. So let's just talk a little bit about course logistics, and then we'll hop into the good stuff. If you haven't seen the Voice AI and Voice Agents primer, I recommend taking a look. We tried to write down what we've learned from 2 years of building real-time multimodal AI stuff. And if you're interested in this course, I think it's at least worth skimming. It's also the genesis of this course. The positive feedback we got when we put the primer online is what led to wanting to do this community thing. Also, you have the course portal in Maven, and we are posting every session. We have 28 sessions so far scheduled. We're going to try to get background materials up before every session, and every session is recorded and available in the portal. So you can attend live, or you can watch the videos, or a mix. Probably a mix, since 28 sessions is a lot, even for me, and I love this stuff. You also can join the Pipe Discord and participate in the discussion there, and I hope you do. I think a lot of the value of something like this is the community, and we're going to work really hard on the community part of this as well as on the office hours and technical sessions. Finally, credits. Really big deal. Super excited about all the people who have offered credits to students in the course. Very grateful. I do not have the credit stuff all worked out yet, but I will get it done in the next few days. So I appreciate your patience. We'll get there. All right. Voice AI today is growing very fast, and it's growing especially fast for telephony use cases. I put a few examples here of things we see a lot, but I'm really interested in seeing new stuff this month from all of you, as well as going deep on this stuff if you're working on it. Collecting patient data for healthcare appointments, following up on inbound sales leads with outbound calls, handling a really increasing variety of call center tasks, coordination of all kinds between companies, which is under the radar, but we see a lot of this use case, and answering the phone for nearly every kind of small business. And what ties all these cases together, in part, in my mind at least, is that they all have a very clear economic ROI, and also, as you start to roll these things out, big, interesting qualitative impact as well. So, for example, in the call center world, voice AI growth is driven first by the calculation that today it's cheaper to answer the phone with a computer than with a person. And so the return on investment calculation is really easy to articulate. But as you roll out this new tech, lots of things get qualitatively better as well. We see now that voice AI agents are able to do a better job answering certain kinds of questions than most human agents can if you have a good RAG system built into your tech stack. And things like wait times go down because one of the challenges call centers have is staffing. It's really hard to staff for peak periods. It's relatively easy to spin up AI agents in the cloud for peak periods. That has big knock-on effects on customer satisfaction and on call center operations. If you're here today, you probably know all this, so we'll jump right in and get started talking about the sort of 4 things I tell people when they are working on getting up to speed with voice AI from the beginning. I usually start by saying you will at some point need to think about three of these things and possibly the fourth. The first is, what are the models and APIs that people are using to build voice AI applications? The second is, how do you write the code for your core voice to voice processing loop and your business logic? I usually call that orchestration, but since 2025 is the year of agents, we could also think of this one as, what's your voice agent framework? Third, how do you deploy and maintain and evaluate and manage and scale your application? Where does your code run? How does it communicate over the network? How do you plug into all of the various tools and systems you'll need in production? That's infrastructure. Fourth, if you're building a non-telephony application, you'll need client-side code as well as code running in the cloud. How do you build web and mobile front ends for real-time AI? Today, we'll talk a little bit at a high level about 1 and 2. Tomorrow, we'll talk about 3, infrastructure, and we'll dedicate a session, probably multiple sessions really, but one focused session on client-side code later in the course. So, what is a voice agent? Let's start talking about models and orchestration by asking what a voice agent actually is. I'm a programmer, so my basic view is that a voice agent is a loop. You take some input, you pass it through an LLM, you generate some output, and then you go back to the beginning of the loop. That doesn't seem so hard, right? Except for low latency networking, turn detection, interruption handling, context management, function calling and tool use, scripting and instruction following, memory and retrieval, integration with legacy systems, and some other things I didn't have room for on the slide. It turns out that a lot of the complexity in getting a voice agent right is in handling between, depending on how you count, maybe between 6 and 10 tricky things. And the shape of these things is unique to real-time multimodal AI. Building voice agents turns out to be quite different from building text mode agents. You need very low latency network transport. You have to solve this problem, turn detection, which we'll talk a bunch about a little bit later and more in the course. Voice interruption handling is a whole thing. Context management works differently for multi-turn real-time agents. Today's LLM tool calling wasn't designed for real-time use cases at all. Instruction following and function calling reliability decline a lot as multi-turn contexts grow. So you have to find ways to compress or focus the context, or at least you have to think through what the ramifications of that are. You often need to implement memory or retrieval augmented generation, but you want to do that without blocking the conversation loop. You need to integrate with backend systems and tools, but again, you need to do that without blocking the conversation loop. So today, the standard architecture for the majority of voice agents in production is a 3-model cascade. A transcription or speech to text model turns the audio into text, feeds that text to a large language model operating in text mode, which outputs text that is turned into voice by a text to speech model. I left the challenging things from the last slide up in the corner so we can keep thinking about them in the context of this architecture diagram. So at each stage of this architecture, you have to worry about some subset of these tricky things, and you have to try to figure out how to make all of these 3 models, and sometimes more than 3, work together at very low latency. So why is this architecture used for most of today's voice agents? We will talk about speech-to-speech models and APIs a bunch during this course, and friends from Ultravox and OpenAI and Google will all talk about their work on speech-to-speech models and APIs. Most people, including me, think that speech-to-speech models are the future of conversational voice. But today, it's easier to achieve reliable instruction following and function calling behavior with the state-of-the-art LLMs operating in text mode than with native audio mode models. The native audio speech-to-speech models are just a bit less capable. And generally, what we're trying to do with voice AI is just right on the edge of the frontier of what today's very best models are capable of at all reliably, that we really need to use the best models we possibly can running in their best mode. There are definitely some use cases where speech to speech models are much better than the three model cascade even today. Language learning, for example, really leverages the strengths of speech to speech models. And I'm looking forward to talking more about all of this with all of you later this month. But a lot of what we do this month will focus on this kind of classic three model cascade. Now, we really can't talk about anything else in voice AI without talking about latency, by which I mean the voice to voice response time in a conversation. This is the biggest single challenge for voice AI developers. Latency is always top of mind, no matter what models we're using, no matter what architectures we're using. Everything we do is driven to a fairly large degree by the need to respond quickly in a conversation. When humans talk to each other, we expect something like a 500 millisecond voice to voice response time. If I say something to you in a conversation, I expect some kind of cue. Either you start responding or you say, or you give me a facial expression or something within a few hundred milliseconds. If I don't get any cue from you in much longer than that, I tend to think there's something really weird about the conversation. And that is also true when humans talk to voice agents. We bring our human assumptions to these voice AI conversations, which is great. But it also means that those of us building this stuff have a very tight latency budget when we build this stuff. Here's a table. This is a screenshot from the voice AI primer. This shows typical line items in a latency budget. And here, these line items add up to just under 1,000 milliseconds. I often aim for about 800 milliseconds in the production voice agents I work on. 800 milliseconds is a tough latency budget to hit. It is possible to hit it at scale and at reasonable cost today. And I've built prototypes and limited deployment voice agents that can hit 500 millisecond voice to voice latency consistently. It's possible, but there are lots of trade offs involved, especially around cost and scaling and quality of output. As all of the pieces of our Gen AI architectures and all our models get better, it's going to be easier and easier to get down to 800 milliseconds and then 500 milliseconds and then even faster. What I will say though is that if you're aiming for 800 to 1,000 milliseconds today, then people are going to be happy talking to your agent. So that's a good rule of thumb to keep in mind. Which AI models are being widely used today in voice AI? If you're choosing models, you're probably thinking about three things: latency, the quality and reliability, the output you get from the models, and the cost. What we see today is actually a relatively small group of models that are used in the majority of production voice AI use cases. On the speech to text side, DeepGram dominated for a long time because they had the best combination of word error rate and low latency. More recently, we've seen a bunch of good work optimizing Whisper, the open source transcription model from OpenAI. Whisper was not originally designed to be a real-time model, and if you just run Whisper using the Transformers library from Hugging Face, for example, you're probably looking at 800 to 900 milliseconds time to first token from Whisper. That's too slow because, as we just talked about, that's your whole latency budget, ideally. There have been a bunch of really nice open source efforts and some good commercial API work on making Whisper faster, though. And by faster, again, I always emphasize I don't mean throughput, time to first token or time to first byte, because that's almost always what we care about more in voice AI. Some of these projects have Whisper down closer to 300 milliseconds or so, time to first token. And at that speed, it does make sense to use Whisper in voice AI contexts. Our friends at FAL and Firework and Grok are all hanging out with us this month and providing credits so we can experiment together with their Whisper APIs. And recently, we're seeing a lot of non-English language voice AI developers use Gladia, which is a really great set of models with support for a huge variety of languages. AI is global, and great language support is really important. I've been super excited to see what Gladia has done in their recent releases. We're using Gladia with a bunch of partners, and Gladia is hanging out with us this month and offering credits too. On the LLM side, we mostly see two models today. GPT-4o has been the workhorse, and more recently, Gemini 2.0 and now 2.5 Flash are very good models and aggressively priced. You can see in the LLM table on this slide the median and P95 time to first token numbers from some of the monitoring we do at Daily. Caveat, these numbers are actually from February. So I need to update this table, but you can see why Claude Sonnet here is not used nearly as much as GPT-4o and Gemini Flash, even though it's a good model. Time to first token has just not been something Anthropic has focused on. If you add 300 or so milliseconds and a bigger P95 TDFT spread to your API calls, that knocks you out of the running for a lot of voice AI today. I really hope this changes, both because I think competition is great, we all benefit from it, and also I personally really like Claude as a model. On the text to speech side, we see Cartesia and Rhyme and 11 Labs most often in the work we do, but there is a lot happening in text to speech. Play AI and Grok have a new partnership, for example, and the Play AI model and Fast Grok inference are a promising combination. They're running a workshop together later in the course. OpenAI and Google are both doing super interesting things with audio models and like a bunch of different things, and we'll have office hours with both of those companies. And there are some great open source TTS projects that we'll also talk about. Now let's talk about network transport, which if you know me, you know is near and dear to my heart. Network transport just means how do you move the audio from the user to the cloud and back. It's worth a little digression. Why do we need to move the audio to the cloud at all? Why can't we just run things on our local devices? There are a couple of reasons. One, if you're doing something telephony related, you don't have a device you can run any code on. All you have is a voice channel, so you have to move the audio to the cloud. And second, we talked earlier about voice AI use cases being right on the frontier of what today's models can do at all. You can't run a really capable LLM on a mobile device or a laptop. That day is coming, but it's not here yet. Once you need to talk to a big LLM in the cloud, you probably should just move the audio to the cloud and run your agent orchestration there as well. We will have a session later in the course about running models locally and about hybrid architectures in which some models run locally and some run in the cloud. I really love thinking about that, and I think all of our tooling will evolve more and more in that direction over time. But we can park that for today and come back to those ideas later in the course and talk a lot about them if from a variety of angles if anybody is interested. So there are three main network transport approaches we use with voice AI today. Most programmers are familiar with WebSockets. WebSockets are great for sending structured data over long-lived internet connections. WebSockets are not great for real-time audio and video for a whole bunch of reasons that we won't take time to go into today. There's a bunch about this in the primer, and we'll do a deep dive session later in the course all about WebSockets and WebRTC and embedded WebRTC. What you should know about WebSockets is use WebSockets for server-to-server audio connections. Don't use WebSockets in production for client-server audio connections. WebRTC is what you need for client-server audio. Audio from the web and native mobile apps to the cloud and back, if you have real-time constraints, is what WebRTC was designed for. WebRTC is a fairly complicated protocol. You generally don't want to write your own WebRTC client or server from scratch. I would argue you don't even want to directly use the WebRTC APIs in JavaScript and in Python. You can use WebRTC libraries that abstract that complexity, though. Pipecat has open source client and server peer-to-peer WebRTC transport modules and also supports commercial WebRTC cloud services like Daily and LiveKit. The Hugging Face Fast RTC framework is a really nice AI first set of what I would call peer-to-peer abstractions on top of WebRTC. So we'll talk much more about this. And finally, telephony. Telephony is a big topic. We'll start to cover it tomorrow because you can't really talk about telephony without talking about infrastructure. I'll just say today that there are two acronyms you'll encounter when you do telephony and voice AI things. It's worth knowing roughly what both of them are. PSTN stands for the Public Switched Telephone Network, which is the infrastructure that allows you to make and receive calls to actual phone numbers. When you buy a phone number from Twilio, for example, and set it up to receive inbound calls and fire off a webhook for you, you're using Twilio as a PSTN provider. SIP is the general set of protocols that are used for interconnecting digital telephony systems. If you need to integrate with a call center telephony stack or the telephone system at a big hospital, for example, you'll need to use SIP. Again, more on telephony starting tomorrow. To close out this big landscape overview, I want to talk a little bit about 2024 problems and 2025 problems. A lot of what all of us were doing in voice AI in 2024 was just putting the basic building blocks together. So you could build a reliable, flexible, scalable agent that was pretty good. That was a lot of work. All those things we touched on earlier today, the turn detection, network transport, and interruption handling, and real-time context management, multimodal data processing. So, for example, we spent a lot of time building those kind of basic modules out in PipeCat early on. We started doing this in 2023. PipeCat started its life as tools we built ourselves to experiment with real-time AI, and then tools we used with our customers. And we probably rewrote all these core pieces 3 or 4 times when PipeCat was still just our internal tools. And then when we open sourced everything and invited other people to contribute, I think depending on how you count, the community rewrote things another couple of times before we all decided that PipeCat was widely used enough and good enough that we really should stop making breaking changes. And I think everybody who was working on this stuff in 2024 kind of went through a similar arc. We had to get the basics right. We had to get the foundation laid. We've done that, and now we can solve harder problems. And harder problems are definitely there to be solved for a bunch of reasons. More and more people are interested in this stuff and are doing more and more things and pushing the boundaries of use cases, which makes all of us more aware of where the boundaries are. And also, LLMs just keep getting better, which means we can do more with those LLMs, which means we have more complex workflows and use cases that we have to figure out how to improve the building blocks for. So here's my short list, the stuff that's top of mind for me right now in, I don't know, a third of the way through 2025. I'm looking forward to hearing what everybody else's top of mind problems are, but I'll just give you mine. Evals. So no matter what you're building with generative AI, evals are basically a huge topic. I think none of us have good enough evals for any of our Gen AI production workflows in 2025 yet. And that's definitely true for everybody I know who's building voice agents. We have a big session on evals next week led by Hamal Hussein, and 3 companies in the course are doing ops and evals stuff from really interesting directions, and we'll hear a lot from them as well. Second, hosting and scaling. Let's take these together for the moment. I would say about this that running voice AI workloads is very different from running HTTP workloads. We'll talk a lot about that tomorrow. I promise that if you love Kubernetes, we've got you covered. Third, workflows and scripting. So, how do you define what you want a voice agent to accomplish? Can you write one really great prompt and let your LLM do its thing? Or do you need to build a bunch of scaffolding, or maybe some of both? We'll have a session on scripting and workflows next week too, and a bunch of people I know have signed up for the course are doing interesting stuff here, and I think this is a great set of conversations to have this month. Fourth, what I've bucketed here as perfect speech. I think it's pretty clear that LLMs operating in text mode have pretty much passed the Turing test, which is a really big deal. And we don't have time to talk about it today, but we should talk about it more, that we now have computers that kind of just blew past the Turing test. I don't think we've quite reached the point where we can say that real-time speech recognition or generation passes the Turing test. We are close, but long-tail issues with both ends, the recognition and the generation, are what I think of as 2025 problems. People talk about this in the PipeCat Discord a lot. So things like accurately recording email and postal addresses is hard in a voice AI conversation. Completely natural intonation and cadence in voice output is not quite there yet. We have many of the pioneering companies in both speech recognition and generation participating in this course. We'll do a bunch of sessions on this. It's amazing the rate of improvement in all these models. We are really close. Finally, I just want to talk a little bit about turn detection. I've been spending a bunch of my time working on turn detection, as much of my spare time as I can. because it's both very important. Like knowing when the LLM should respond to the person is both very important for the kind of qualitative experience of a voice AI conversation. And this is also a fun and hard machine learning problem. A bunch of us have been working on a completely open source, open data, open training code, native audio, turn detection model. We can talk about what all those things mean. If you're interested in training small models or interested in really improving your voice AI conversation performance, we'll do a session on this model. You can look at the weights on Hugging Face, the training code on GitHub. The model is hosted by our friends at FAL. You can self host it as well. It's easy to integrate with whatever your voice AI tooling is. There's a link on this slide to the PipeCat integration docs. This is a big topic for me right now. Finally, I want to highlight that in the second half of the course, we'll have several sessions about topics that I collectively think of as what's next. Real-time video, running models locally, programming with your voice, on-device models and hybrid architectures, as we talked about before. More on those sessions soon. A bunch of them are on the course calendar. If you have a topical session you really want us to do live, let me know. Happy to add anything that there's interest in. And of course, we'll also talk about all this stuff in the Discord. So that's a wrap on my slides today. We have time for questions. I will stop talking and stop screen sharing and check the channels and let my colleagues who are here moderate a little bit and suggest questions and topics.
Thanks for all the great questions in the Discord. We also are scanning the Zoom chat here. Great if you can pop over to Discord and ask some more questions there. Quinn, I just slapped you a doc with the rundown to make sure we get to everyone's questions. Chad, please, others tap in if there are questions to flag, but maybe we can start with a couple. Right at the top, there were various questions about latency, Quinn, with folks commenting, for example, how impressive 800 milliseconds is. Chad dove in and explained that we aim for 500 to 800 millisecond latency with Twilio PST and telephony or browser WebRTC. Do we see latency with both transports? And then someone specifically asked, looking forward to learning how to reduce that latency a lot while also preventing interruptions, a problem we've had.
So there are a bunch of pieces here, and we should talk probably more about it than we have time for. I agree that 800 milliseconds is, for most production agents that are using public APIs for inference, aspirational but achievable. I think it's fine if you're more like 1,000 today. People are okay with that. But if you think about it as our target is 800 milliseconds, I think it's a good forcing function for kind of pulling all the latency out of all the pieces of the pipeline you can. Sometimes things will be slower because you have a spread in your inference responses from your API providers, or your user is on a poor network connection and the WebRTC jitter buffer has expanded, or you have a couple of hops in your telephony network and they each add a few tens of milliseconds. So one thing I would just say is that measuring this stuff regularly from the client side is really valuable. And if you see published latency numbers, they are almost never latency numbers published from the client side perspective, because all of us who are running infrastructure, it's much easier for us to monitor the latency of pieces of our infrastructure than the end-to-end latency from clients. So if you're building a voice AI app, record the conversation with a separate microphone, stick the audio track in an audio editor, and just visually look at all of the gaps between the waveform when the user stops speaking and the waveform when the agent starts speaking. I always tell people to do this, and people are like, oh, I didn't think of doing that. I'm like, you didn't have to build any more tooling to actually see what your voice-to-voice latency really, truly was. Just do it by hand. You can build tooling for it, but it's actually quite hard to test the voice-to-voice latency from the client. But if you don't test it, you don't really know what it is, because as the question about PSTN suggests, like, how do you measure that? You don't have any code running on the phone that made the call. So make a bunch of test calls, try to make test calls from different regions and different cell phone providers if you can, and actually measure the latency. Reducing latency while preventing the bot interrupting you a lot I think is the question here, the third question here that Nina highlighted. That really does come down to better turn detection. There are a bunch of things you can tweak in your voice activity detection kind of configuration if you're just using a traditional VAD based turn detection. But moving towards like acoustic and semantic information being part of the turn detection judgment is the kind of unlock or the cheat code here for getting fast responses, but few unnecessary or sort of unnatural interruptions. And that's why a bunch of us are working on these turn detection models. OpenAI shipped a text mode turn detection model inside the real time API. I think it's quite good. Tavis, which is a company participating in this course, has a really nice audio turn detection model inside their API. There's the open source audio turn detection model that we've been working on as a community. There are people who are in production using Gemini Flash in audio mode as a turn detection engine, which actually works very well. It's just slow enough you have to run like a parallel pipeline and greedily inference or optimistically inference. So there's a bunch of approaches to turn detection. Maybe we should just start a whole Discord channel on turn detection.
Could you talk to the difference between text-based turn models versus native audio? You referenced that, so I was looking for some more context. And
Yeah.
in Discord, some folks were specifically asking, for example, about the live kit model and the pipe cat model.
Oh, sure. Yeah. So the live kit model is a great example of a text based turn detection approach. It's a fine tuned model trained on top of the small LLM, very small large language model. And it's fine tuned to do a turn detection based on prediction of end of speech. That gets you a lot of kind of grammatical linguistic information. It doesn't get you audio cues. A bunch of us think that you just have to have the audio cues to do reliable turn detection. So that's the approach that the open source model we've been working on takes. You feed that model audio fragments, just like you're feeding your voice activity detection model audio fragments, and the model operates directly on the audio. And the current version of the model uses a model that Meta released a couple years ago called Wave2Vec 2 BERT, which is the foundation for a bunch of audio classification stuff in the machine learning world. And the really cool thing about Wave2Vec 2 BERT, like it's a pretty standard conformer based model, which is like an audio transformer architecture, but it was trained on 4.5 million hours of multilingual audio input. So the theory is, and nobody really knows how machine learning models work. So like I'm free to have a great theory. The theory is that when we feed a bunch of turn detection specific data sets through a training process on that model, we're getting two things. The model is learning acoustic patterns, like if I draw out a word, or if I have a rising intonation, or if I have a particular sort of pattern of syllables at the end of my phrases that indicate that I'm not done talking, the model is learning that. The model is also, we're also leveraging all the weights in the pre-trained version of the model that have to do with like language structure. So we're also getting the language structure stuff that you get from a text-only approach. And I think in all machine learning contexts, like being able to train a model end to end for a task is really valuable. So we're going from audio to the turn classification without a transcription model separately breaking the training loop there. For example, if you feed most of the text mode experiments in this regard, transcription without punctuation, they don't work at all. The audio model just doesn't care.
Early on, fairly early on, people were asking about models. What's the preferred model for voice agents? For example, someone asked, are folks also using GPT-4.1 for voice use cases, or is GPT-4o still preferred?
You still see mostly GPT-4o, and I think there's a couple reasons for that. One is big model changes do require some work on prompts, which suggests that you really need good evals. None of us have great evals. It's not just a thing where you can drop a new model in and be 100% sure it works. So it takes a little bit of time to adjust. I also think that the trade offs that the labs are generally making when they release models are just not optimized for what we do in the voice AI space. In general, a lot of what we do in voice AI is out of distribution of the big model training sets right now. So I don't see better results in my evals of 4.1 versus 4.0 for what I'm mostly interested in. So there isn't a good reason to switch yet. Now that may change as more 4.1 checkpoints are released, but 4.0 is still, I think, the workhorse. The Gemini models are really good, like really good. A lot of people are moving towards using Gemini for some or a lot of their voice AI workloads. And I think over the course of the year, there's going to be a lot of experimentation with Llama 4 and the Quinn models and other open source models because the mid sized open source models are getting better and better. You can, for example, fine tune the Llama models to do specific workflow things in a really nice way that is harder to do with the big models. Arguably, it's a whole nother conversation, fine tuning. But we are going to have a session on fine tuning led by the folks at OpenPipe who have a great fine tuning platform. I would say that we're still seeing 4.0 and Gemini 2.0 Flash. I think people will move to future OpenAI models, but I don't know when. And Gemini 2.5 Flash is so new that I don't have a great opinion on how much better it is for what we're all doing with voice AI yet.
A member noted 4.1 mini is worth upgrading to, but needs prompt updates. And then I'll add a second question about models. What is the best LLM voice model for reliable tools calling?
So I think it's a race depending on exactly how you prompt them between 4.0 and Gemini 2.0 Flash in my evals. I had a long and really good conversation with Zach from Ultravox about making Llama 3 good at tool calling, and he's going to talk about that later in the course. I was a little more skeptical, but Zach has done a ton of work on that, which I found super, super interesting. But I would just say that if you need the answer today and you don't have a ton of experimentation time, that 4.0 and Gemini 2 Flash are both quite good at tool calling, and they're a little bit differentially good. I know Brooke from Koval has done some evals here and published them. We can find a link to what she did when Gemini 2.0 Flash was still in beta because it's definitely worth reading. That reminds me a little bit of the 4.1 mini comment here, Nina. I'm excited to hear that somebody's getting great results from 4.1 mini. We should add it. I would like to add it to our monitoring at daily. I felt a little bit burned by the 4.0 mini cycle where for a long time 4.0 mini was actually slower than 4.0. So cheaper, but slower and massively worse at tool calling and function calling and instruction following. So I felt like that was not a good trade off for voice AI. I think they were just optimizing for compute scalability internally at OpenAI. But a bunch of people would say to me, "Oh, we're going to use 4.0 mini because it's faster." And I was like, "It's not faster if you use it, but not for that reason." Which again, I think highlights how useful it is to do a lot of monitoring of this stuff.
Was asked in the Discord, are there good ways to use multimodal models like Gemini to evaluate the tons of text to speech models?
That's such a great question. LLM as a judge is like a whole thing. I don't know for sure if you can evaluate everything you want to know about a speech model using an LLM, but you can definitely evaluate a lot. And Koval, which I just mentioned, started out as Brooks' work at Waymo building really big simulation driven evals for real world AI use cases, self driving cars in that case. And Koval has a bunch of simulation tools that use LLMs to judge how conversations succeeded or failed with different prompts in development, in production. It's definitely worth talking to Brooke about LLM as a judge stuff. I do think Gemini in audio input mode is super impressive. The best audio understanding model, in my opinion, is Gemini 2.0 Flash and now 2.5 Flash. So if you are operating in audio input mode, those models are the ones I reach for first. I published a few examples of using Gemini in audio input mode and then in a parallel Pipecast pipeline doing transcription also with Gemini to get you some of the audio understanding without using the full cut down, less capable speech to speech model or API. It felt like a little glimpse of the future, but also a little bit more of a complicated pipeline. But I know some people are actually using that approach, sort of Gemini in audio input mode for voice to voice use cases in production.
D. Vasquez asked, we built an agent using daily Pipecat with a pipeline of speech to text, LLM, TTS, and was fine. However, we needed a pipeline with voice as input and text as output, and we were not able to do that. It seems the Pipecat pipeline really needs voice as input and output, or probably we were doing something wrong. Is there an example of Pipecat for STT LLM? We needed this for a text chat that accepts voice as input.
Yeah, you can definitely do that. It's just a little more code to make sure you're handling the text input modality at the top of the pipeline. Whatever pieces of the pipeline need to run when you get text, you just have to wire it up. In the Pipecat world, I think we should probably have better examples for that because we do a lot of that. A bunch of people do a lot of that, but I don't think there's a great code example for it. This was for text input in addition to audio input. Did I understand the question?
I think it was audio input and text output. The trick there is the LLM is going to stream its output, so you need to write an aggregator. We have built-in aggregators in Pipecat that you can use. So that's just one trick. When you use a TTS service that has aggregation built in. Yeah, I think maybe just an example or two would probably be helpful there, but it's
Yeah,
certainly possible.
say more about what you're working on because we may actually have sample code for it and just need to dig it up and point to it.
Okay, great. I wanted to come back to something that was asked early on in the session. Someone's asking what models are good for Arabic. And
Hmm.
a member just replied, voice-to-voice model, Gemini Live is really good for Arabic. It's great.
And other models that come up when we do stuff with people in the Arabic speaking world are Gladia on the input side and Play AI on the output side.
Some questions related to flows. Actually, there's been one question about telephony. So let me ask that really quickly because I know telephony is really key to voice AI use cases. What about integration of VoiceBot with open source telephony like Asterisk?
Totally doable. And in fact, I know from conversations with people that there are people who are using Asterisk and other open source SIP stacks with Pipecat. You can do it a few different ways. One way is to use SIP over WebSockets. As far as I know, nobody has submitted a PR to build a transport that's specific to Asterisk that's easy to get started with. It would be great if somebody wanted to.
For flows, because it's interesting to talk about voice agents in production, I know. Here's one question. How do we reduce the initial connect or startup time with the bot? Even after using reserved instances resolving cold start issues, it still takes 20 seconds. Any suggestions on this, how to reduce the startup time connection with the bot? And then I think another member hopped in and made the good point that one way to address that in the real world use case, and sorry, I'm scrolling up in the Zoom. I think someone mentioned the nice little workaround of playing hold music, for example.
Yeah, there are lots of workarounds everywhere you have latency issues in the world, but solving the problems for real means solving cold starts. Often people want to use something like AWS Lambda, which feels like it's largely solved cold start issues, but doesn't have any kind of tooling that works for voice AI. Same thing for Google Cloud Run. If you're hosting your own infrastructure, there's both optimization of how fast things start and there's running a bunch of spare capacity. Those are basically the two things you can do. We've been working on that a lot in kind of the hosted agent platform we just launched called Pipecat Cloud. Our goal is to get cold starts down below 10 seconds and to have enough spare capacity across what everybody is doing on our platform that you rarely see cold starts after 0 to 1. But we also have to give people knobs to turn, like allocating spare capacity preemptively, like with a REST API call, if you know you're going to have like a big traffic ramp up. I don't think there's any magic to it. It's just optimizing how fast everything starts in your whole stack and running enough spare capacity, which has an economic calculation. Mark will talk more about this stuff tomorrow just because it's stuff we think about a lot these days. And 20 seconds is not fast enough for voice AI agents. It's a lot faster than the serverless GPU clouds can usually start things. Although Michael from Cerebrium has done a lot of really cool cold start stuff on Cerebrium, and we'll get him to come talk about that stuff in the kind of serverless GPU world.
There was an exchange about creating interaction scenarios, i.e. workflows. What about creating interaction scenarios, branching in advance with LLMs, simulating answers and preparing TTS answers in advance? Also building questions in conversation in a way to get simple yes/no answers, recognize them fast, and based on prepared branching, replay hypotheses and collect feedback. And that was the question. 2 links were shared in response. Vappy has great tooling for this. And there's also Pipecat flows. Quinn, I think Vappy will be doing an office hours. Is that right?
Oh yeah, and we can pull the Vappy folks in for any of the conversations. They've done a lot of really good work on all parts of the stack, including their kind of graphical workflow builder tool. And Pipecat Flows is an open source graphical or not graphical if you just want to write JSON structures for building a state machine view of a branching conversation. I think there maybe were two questions there, which is like, how do you represent a branching conversation? And then maybe the second layer of that is, can you do speculative inference kind of loosely on a branching conversation? I have not seen anybody do like greedy or speculative inference beyond just trying to get a very fast response from the current voice utterance. It's an interesting idea. Koval is doing it in simulation for evals. That's very different from real world conversations. What people are often doing is greedily inferencing before the turn detection fires, which can include using the interim transcription results if you're using a transcription model that will give you interim results. That is helpful. It is also more costly. So you're trading off whether you want to double your LLM platform costs versus whether you get a good speed bump from doing speculative inference. Maybe we should talk about like speculative inference down a defined state machine. That would be fun.
Someone recommended to the person who was asking about voice AI in Arabic, you may want to check out Hamsa, I think. Try Hamsa, HAMSA.com. That's very cool. And then also, Peter noted a tip for Gemini. If you want accents, specify the country language in your parameters. It will actually change. UK, Australia, English, USA, etc.
A question in the doc about examples of voice AI that handle multiple speakers. I have not seen an app where somebody has done enough work to handle multiple speakers really well. I think it's super interesting. We've played around a little bit with it for games, things like choose your own adventure storytelling games where you have a couple people playing the game together. It's hard because the transcribe and then fire off inference or feed audio to an audio native LLM and then expect it to do inference just doesn't map very well to a conversation that's more than a one human and one LLM conversation. So you have to define like what you want. What are you even trying to do in a multi-person conversation given the assumptions about the APIs and the model training and the model architectures today? I think it's a super interesting area. We talked a lot to the folks at OpenAI and Google about the evolution of their models and APIs, and they're just starting to think about having their models know when they should respond and when they shouldn't respond. It's a very large surface area problem, but hopefully, as the models move in that direction, they will incorporate things like, oh, there are multiple people talking. I need to factor that into whether or not a response is useful now or whether I should just emit a no response token. We're really early days for kind of the next generation of model data sets in the big labs that really exercise the broad set of like voice AI potential use cases. Just so people have like links to follow up on as we get into all of these sessions, Free Play, Weave, and Koval are three LLM ops slash evals slash observability tools that all come at this domain from a different angle. I think they're complementary. We know the teams building all of them, and we really like those teams. So those are the three I reached out and asked them to hang out with us and give people credits and do office hours. So all three of those tools I think are very much worth looking at, and their teams are going to be in the Discord and doing sessions. Thank you, everybody.
Thank you all. So as Quinn was saying, check the Discord. If you have problems getting into the Discord, you can ping us at daily and we can try to help figure it out. In the Discord, we'll post more information about the next section, next session, and course material. Thank you all.